Welcome back to Algebra 1. We are in section 3.1 where we're beginning to work with variables. But first, I do need to say that this new book that my young friend gave me so that I would have an inexhaustible supply of lame jokes for you is truly among the lamest that I have seen. So first, what would you call 3 feet of trash? Well, it is a junkyard. And now, why did the garbage truck look so sad? Well, it was down in the dumps. So, variables, page 87 on our text. And I'm going to refer to the book a lot here because see this whole first page here? That same page in your book. There's just a lot of text. I'm not going to read it to you. I assume that since you're in my algebra class, you know how to read. But we are starting off with an example of basic use of variables in algebra. Now, there's a Sunday school class that's having a party, and they have been asked to find the price of root beer, Coke, and Sprite. And it's 75, 70, and 65 cents would be the price difference in the cans, and the cost of these 3 different varieties of soft drink. Down here in Texas, I would say the 3 types of Coke. What type of Coke do you want? Root beer, Coke, or Sprite? But 3 different types of soft drinks. And we wouldn't actually break them apart. We'd say whatever you want, it's all the same price. It would probably be like $1.50, not $1. But the Sunday school committee wanted to know, okay, we've got 62 people that we are going to be offering a drink to, and I want you to give us a cost breakdown for each different type of soft drink so we can determine what it is that we want to offer as the one soft drink. And you can see how they really stretch the examples that they have in your book, but it still accomplishes the purpose. So let's say that the price of the can, we're going to use a little P. P stands for price, and the total number of people that we have at this Sunday school picnic is 62. So if you were just not even thinking about algebra, you'd say, okay, if one can costs 75 cents, well then the way that I figure out how much it costs for everybody to have is I just take 62 times 75. If I want to know how much Coke, how much it costs everyone to have Coke, it's 70 cents times 62. If I want to know how much it costs for Sprite, I'm going to take 62 times the price, which down here is 65, and that's what these total prices are. So this is the breakdown that they wanted. 62 times 75, 46.50. 70 times 43, 70 times 62 is 43.40. Finally, 65 cents times 62 would cost $40.30 if you got Sprite for everyone at the party. What you've actually done, this P here is what they call the variable, because when you have variable wind speeds, it's not blowing constant speed the whole time, but it goes fast and it slows down and then it goes away and it's fast again. It's variable. The price that we're calling P, it varies according to which type of soft drink we're talking about here, Sprite, Coke, or root beer. The price varies. It can be, in this particular problem, it can be 3 different prices. So the set, if you will, of soft drink prices would be the set, and I'm just going to go ahead and use the cents notation here, 65 cents. I'm not going to do the decimal. 70 cents and 75 cents. So when we're calculating how much it's going to cost us for these soft drinks for this problem, these are the only possible values that we can have for the cost of a soft drink. Now, is there a soft drink out there that costs 50 cents? Well, yeah, you go down the street and you get this brand X thing of really nasty tasting grape soda, and maybe it's 50 cents. You go down to this little boutique place and they're really proud of their label of a root beer, handmade root beer or something, and it's $2 a can. So even though you have these other choices that are out there, the only ones that work for this problem are the prices 65, 70, or 75 cents, and that's because it's this particular set of possible values for the variable, and that is called the domain of the variable, D-O-M-A-I-N. This is the domain of the variable. The way that you figure the price, obviously, is you take the total number of cans of soft drink that you're going to have, and you notice it's 62. It doesn't change. It's not 62, 70, 93. It's always and only 62. And you multiply that 62 times the can price. But because the price of the cans can change, we're going to use this letter here, this variable, letter P. Usually we try and make the letter that we select have a meaning to it, or frequently we do. If you get lazy like me, I have it be X for everything. But here it makes sense that we would use P for our variable, because what we have is the price per can. So this right here is called an algebraic expression. What makes it algebraic, that we can really stand out to us that it's an algebraic expression, is that it has variables in it, or expression. This number here, that's 62, that stays constant. It doesn't matter if you get Coke, if you get root beer, if you get Sprite. You have a constant number of people. It's 62 people. The numerical part of this algebraic expression, reasonably enough, is called the constant. And the P, the letter part, the part that is going to go up and down, the part that's going to change, is called the variable, because it varies. And what we'll be using lots and lots and lots in algebra and through all of your math classes from here on out, or through certainly the vast majority of them, is we'll be using letters to represent the relationship between other numbers, between bits of data that you've been given. So you will be using algebraic expressions, and they will consist of two parts. They will have the constant part, and they'll have the variable part. The constant part is just the number. Now what happens if this had just been P by itself? What would the constant part be? Well, you don't see it, but you know that if there's not a number in front of P, then we're just talking about one P. So we have 62P. This is the introduction from 3.1 to variables. Let's go ahead and see what else we might have. Okay, I've talked about variables. I've talked about constants. They're constant. Another way to think about that might make better sense to some of you is it's a fixed number. It is immovable. It's stuck right there. It's not going to change. That number is fixed in place. It's 62, 62, 62, 62, not 61, not 62 and a half, but it's constant, or it's fixed at 62. So now, I said this was an algebraic expression. Let's see what your text says an algebraic expression is. On page 87 it says, an algebraic expression is the result of performing mathematical operations on any collection of variables and constants. We've got a mathematical operation here. When you have the constant that is bumped up directly against the variable, what does that say? Is that 60? What does 62p mean? I don't think about needing to break this down because I've done it for so long, but when you have the number right up against the letter, that means we're saying 62 times p. Well, does that mean that I have 62 little green peas rolling around? Well, if p actually meant the little green pea, but no, it's 62 times whatever price value from the domain we're choosing to use. So it can either mean 62 times 65 cents, 62 times 70 cents, or 62 times 75 cents. So that's all that's involved in evaluating this algebraic expression. So let's go ahead and do a couple of examples, and then we'll be done with section 3.1. This really should be review to the vast majority of you. If it's not review to you, it still should be straightforward. If it's not straightforward, even after you've read your material, then get in touch with me, okay? Example 1. If C represents the cost of 1 pencil, what is the cost of 10 pencils? So we're going to want to just get in the habit of saying, making this little sentence type thing. When we're defining what our variables are going to be, let's just say let the variable, in this case, say let C be equal to, what is C going to be equal to? The cost of, 1 pencil. And they picked C because they went with cost. So if C is the cost of 1 pencil, how are we going to figure out what 10 pencils cost? Well, 10 times the cost of 1 pencil is 10 times the cost of 1 pencil. So all we have to do is put in here 10 times C. Now let's say that we have 3 different stores we can go to where we buy these pencils. And here we have the cost, which is going to be our domain. We can go, and they're 15 cents at one place, they're 10 cents at another place, they're 50 cents at another place, and that is just horrific writing, but you understand what I'm talking about. What are the pencils going to cost at store A? Well, it's going to be 10 times this value from the domain, 10 times 15 cents. Which is 150 cents, $1.50. This one here, what is the cost of the pencils at the second store? 10 times 10 cents, or $1. And what's the cost of these really fancy pencils with the flashing lights on them and the wailing siren that are 50 cents each? Well, if you want to get 10 of those, it's going to cost you $5. And that's all that is involved in working with these. We pick a variable, and then we say, okay, I want the letter that I'm going to use to be this letter. And this is exactly what the letter means. I'm picking C, and I'm defining C to be the cost of 1 pencil. That's all you have to do. Okay, now this thing goes on and it says, example 2, if the domain for C is 5, 10, and 17, what are the prices? Well, I made a domain of C that was 15, 10, and you should really put those in order within your set, beginning with the lowest and increasing towards the highest. So I picked a domain, instead of the domain being 5, 10, and 17, I picked 15, 10, and 50. What's the cost of the pencils be? Well, if 1 pencil costs 15 cents and 10 is $1.50. If 1 pencil costs 10 cents, 10 cents of those pencils cost $1. 10 of those pencils. Likewise, 10 pencils at 50 cents cost $5. And that's the example that they're going through, just with different numbers in the domain. Remember, you have got to know this vocabulary. The domain is the set of possible solutions, possible values, domain. So I'm going to say the set of possible values for your variable. Possible values for the variable. Now frequently, there will not be a limit to the possible values. It's just specifically when you're dealing a lot with cost and with purchasing or with colors, things like this, your possible choices are going to be very limited. You can have this meal, this meal, this meal, this meal, this meal. And that's all your choices. You don't have an infinite number of choices. But frequently, what will happen is that your list of possible choices or your domain will be all of the whole numbers. Starting at 0 on up to infinity, or maybe it'll be all the negative numbers, or maybe it's all of the integers. So most frequently when you are working with variables, your possible values for the letter, the size of the set that represents your domain, the size of this domain is the majority of the time virtually infinite. So you need to be aware of that. Let's do one or two more right here. This is example number 3. And we are on page 88. Page 88 says, write an algebraic expression to represent the sum of 5 and any real number n. Sum of 5 and any real number n. Okay. First thing, even though they're telling us that we're going to use n as the variable, they're telling us that it's going to be a real number. Let's go ahead and write our little definition anyway. Let's say let n equal any real number. So what is our domain? What is our list of possible values for the variable n? Well, it's the infinite set. It's any real number. Anything that can be, anything that's not a complex number, which is next class. Let n be any real number. So what is sum talking about? Sum, S-U-M, is the answer to an addition problem. Vocabulary once again. The sum of n, any real number, and 5 would just be n plus 5. And this value here is going to vary according to what you pick for n. And that doesn't look like an n. Let me make that a little more noticeable. N plus 5, if n is 0, the value is 5. If n is 1,000, the value is 1,005. If n is a negative 5, the value is 0. So you see how the answer to this algebraic expression is going to change. Algebraic expressions consist of letters and numbers. Well, this is an algebraic expression here. Talked about last time, you could even more narrowly define that as being an algebraic term, a single term, algebraic expression, more than one algebraic term. Now, here's another example of what you're going to want to be doing in your homework. For section 3.1, this says, if the domain of x is the set that consists of the elements -5, 1/2, 2, and 3, find the corresponding values of x plus 9. Well, how are we going to find the corresponding values of x plus 9? Well, remember, if we didn't have this limit right here, the only possible values that we can use for x would be -5, 1/2, 2, and 3. We would write from now until we die. And we would never come up with the complete list of solutions because you'd have an infinite number of solutions. But because our domain has been limited, because the possible choices for x have been limited to -5, 1/2, 2, and 3, there can only be 4 possible solutions to this expression. First, what is -5 plus 9? -5 plus 9 is equal to 4. 1/2 plus 9, that's equal to 19/2. Is that true? Yes, it's equal to 19/2. 2 plus 9 is 11. 3 plus 9 is 12. And you see that those are the only possible solutions. So if the domain of is the set that consists of these 4 values, then we could also write, using set notation, the solutions to this. And you could say that those solutions are the set that contains 4, 19 halves, they say 9.5 in your book, 11, and 12. So you will be doing a fair amount of this in your exercises as well. That's all we have for section 3.1.